Okay, so today we're going to be talking about calorimetry. So calorimetry is a study to be able to measure the specific heat of objects. So if we go back to the equation that we had used before for finding the energy, we did this yesterday, we have the energy that is absorbed or released by an object under heat is equal to the mass of the object times the Cp, which is our specific heat, times the change in temperature. Well, the mass we can measure. We can take the object and put it on a scale and measure it. We can also measure the change in temperature by taking a thermometer and measuring what the change is when heat is added. But this value right here is non-measurable variable. And so for us to be able to figure that out, what we do is we have a science called calorimetry that allows us to determine the specific heat of a substance. And what we do is we know by the law of conservation of energy that energy cannot be created or destroyed. So the energy of a substance here plus the energy of the other substance equals a constant, which is zero. So pretty much the change in energy is zero, just like we did when we talked about mechanical energy. So if I use the equation right here, this equation mCp delta T, and I'm going to use it of the object A. So the energy that is absorbed or given off by object A is the mass of object A times the specific heat of object A times the change in temperature of object A. And it has to equal the negative of the mass of object B times the specific heat of object B times the delta T of object B. And that means we're going to bring this over here, so QA would equal negative QB. Okay, so the other thing that we know is that the delta temperature is just the final temperature minus the initial temperature. Right here, the delta is the final minus the initial. Well, if we put two objects together or one object in the other object, that final temperature is going to be the same of the two objects. So if I take a hot piece of material and I stick it in water, when there's no more change in temperature, those two objects are going to be the exact same temperature. So we know that the final temperature of object A has to equal the final temperature of object B. So I can put the same as just a final temperature. Okay, so I no longer have to specify whether it's object A or B, it's just a final temperature. Well, this bit of information right here is going to be able to be used to find the specific heat of an unknown object. But we have two unknowns. We have the specific heat of object A and the specific heat of object B. So if we compare it with the specific heat of something that we do know already, then we can solve for the specific heat of the unknown object. Well, we know the specific heat of water. So if we compare this to water, then we can solve for our unknown. So let's try an example and you'll see what I'm talking about. Okay. So I have a metal bolt, and I don't know what the specific heat is. Oh, I take that back. We are given the specific heat of the metal bolt. But I have a 0.05 kilogram metal bolt, and it's heated up to an unknown initial temperature. So we're heating it up, but we don't know what temperature it's heated to. It's then dropped into a calorimeter. Okay, so a calorimeter is just an object, like a cup, an insulated cup, and it's filled with water. So we have this calorimeter, it's filled with water, and then I'm going to put the bolt in there. So here's our bolt, and we're going to stick the hot bolt into the water, and we're going to find out, well, what is the change in temperature? So let's figure out what's going to happen. So this bolt now is going to go into the water, and then we're going to find out what that change in temperature is. So we have a 0.05 kilogram metal bolt right here, that's given over here, is heated to an unknown initial temperature, and that's what we're looking for, the initial temperature of the metal bolt. It's then dropped into the calorimeter that contains 0.15 kilograms of water. So we know the mass of the water, 0.15 kilograms. With an initial temperature of 21. So we've measured the water, we've put it on a scale. We also put a thermometer in and measure the temperature of the water. The bolt and the water then reach a final temperature of 25 degrees Celsius. So I put the thermometer in there. When it stops moving up, I know that's our final temperature. If the metal has a specific heat of 899 joules per kilogram degree Celsius, find the initial temperature of the metal. So right here, we're going to write down all of our knowns. And I like to put it in two columns here. So we're going to be dealing with all the metal, and then we're going to deal with everything of the water. So we know the mass of the metal, 0.05. We know the mass of the water, 0.15. Both of these are just measured values. We know the specific heat of the metal is 899 joules per kilogram degrees Celsius, and we only know that because we got it off of a chart that is in our textbook. Okay? We also know the specific heat of water, which is 4180 joules per kilogram degrees Celsius, and that also comes from a chart in our our chart in our textbook. So we also know that the initial temperature of the water is 21 degrees Celsius, and we know that the final temperature of both the water and the metal is 25 degrees Celsius. So what we're going to do is we're going to start with our equations. We know that the Q of the water has to equal the negative Q of the bolt. So what happens is all the heat that's in that bolt, because the bolt is going to be up to a higher temperature, is going to be released, and the water is going to receive that heat and that energy. So we can say that the mass of the water plus the CP of the water is equal to the delta T of the water. And that is equal to the negative mass of the bolt, the negative CP of the bolt, plus the change in temperature of the bolt. Okay, and what we're looking for is that's initial temperature. So we have mass of the water, CP of the water. We have T final minus T initial of the water equals negative mass of the bolt, CP of the bolt, and T final minus T initial of the bolt. This is what we're looking for. So if we plug in everything that we know the mass of the water right here is 0.15 kilogram. We know the CP of the water, 4180 joules per kilogram degrees Celsius. And we know the final temperature of the water is 25. We know the initial temperature of the water is 21. So what happened to the water? The temperature went from 21 degrees to 25, so the temperature went up of the water, which means it's receiving heat is being added into the water. The bolt, we know the mass of the bolt. We know the CP of the bolt is 899. We know the final temperature of the bolt is 25 minus this unknown initial temperature of the bolt. So if we do some calculations, we can get a number over here, which ends up being let's see here, little calculations here. If we end up figuring it out and doing some math, you have the T initial of the water ends up being 80.86 degrees Celsius. So all you're going to do is you're going to multiply these two together and multiply it by 4, divide it by 0.05 and 899, and then you're going to solve for TI. So you can find out the initial temperature of the bolt was 80.86 degrees Celsius. Okay, let's try one more problem. Okay, so what is the final temperature when 3 kilograms of a gold bar at 99 degrees Celsius is dropped into 0.22 kilograms of water at 25 degrees Celsius? So here's our calorimeter, and it's just filled with water. So we have the mass of the water, we know the CP of the water, and we also know the initial temperature of the water. Okay? And then we have a gold bar. Well, we know the CP of the gold, we know the initial temperature of the gold, and we know the mass of the gold. What we're going to be looking for is what is the final temperature, so we put this gold bar in there. Now, the gold bar is 99 degrees, the water is 25, so what's going to happen is this heat from the gold bar is going to be absorbed into the water. And so we're going to assume that the temperature is going to be somewhere between 99 and 25 degrees. So we're going to say that Q of the gold has to equal negative Q of the water. So we have M of the gold, CP of the gold, and T final minus T initial of the gold. And this is going to equal negative mass of the water, CP of the water, and T final minus T initial of the water. This T final and this T final are the same because the gold in the water is going to be one thing. Okay, so we know the mass of the gold is 3.0 kilograms. We know the CP of the gold is 129 joules per kilogram degrees Celsius. We know the T, or we don't know the T final, that's what we're looking for. We know the T initial of the gold, 99 degrees, and then is equal to the mass of the water, 0.22 kilograms. CP of the water is 4180. T final is the same for both of them, minus the initial, which is 25 degrees. Okay, so if we figure this out, and this is just going to be heavy in math, but if we figure out the numbers here, we're going to be able to multiply the the 3 times 129, and we end up with 387. We still have T final minus 99, and that's going to equal, let's see, the 0.22 times 4180, which is 919.6. TF minus 25. And then if we do some distributive property here, we're going to have 387 TF minus 38313 equals 919.6 TF minus 22990. And if you put the TFs together on one side and the constants together on the other side, you end up with your final temperature is 46.92 degrees Celsius. Okay, so this is the concept of calorimetry, and we are going to be working on these tomorrow in class. Don't forget to do your assignment, and we'll see you tomorrow in class.